All right, hello everyone. Today we are going over lesson number 12, which is on properties of photons in the Unit 3 AP Chemistry curriculum. Today your understanding is that spectroscopy can determine the structure and concentration in a mixture of a chemical species. The learning objective is to explain the properties of an absorbed or emitted photon in relationship to an electronic transition in an atom or molecule. And your essential knowledge is that when a photon is absorbed by an atom or a molecule, the energy of the species is increased by an amount equal to the energy of that photon. So when an atom absorbs a photon, it's like giving the atom a burst of energy, and its electrons are going to jump to a higher energy. And then in that high energy state, it's super unstable. So eventually it will go back to its ground state. And when it does that, it's going to emit a photon of equal energy. And then finally, the wavelength of the electromagnetic wave is related to its frequency and the speed of light by the equation C equals lambda V. So let's go through the main ideas of photons. Number one, photons carry energy. So they're like little energy packets of light, and their energy depends on how fast the wave is oscillating, or the frequency, or on its wavelength. And we can calculate that using E equals hv, which is the energy equals Planck's constant times the frequency, or we can combine that with C equals lambda V and use an overall equation of E equals Planck's constant times the speed of light divided by wavelength. Point number two, atoms and molecules have quantized energy levels. Electrons and atoms don't get to move wherever they want. They have fixed specific energy levels. So if you were to picture a ladder, it's kind of the same concept where you can only stand on one rung or the next on the ladder. You can't actually balance halfway in between. And that is the same way with electrons and atoms. So what happens if a photon comes along with just the right amount of energy? Well, if that hits an atom, the atom is going to absorb it, and the electrons in that atom are going to jump into a higher energy level. That excited state is now super unstable, and the electron doesn't want to stay there because it wants to remain stable. So in order to get back to stability, it's going to fall back down to its original ground state. And when it does that, it's going to give off a photon of the same energy. So a photon comes into the atom, it gets excited, it goes back to its ground state and emits a photon of the same amount of energy. So the key idea here is that the change in energy of an atom is exactly equal to the energy of the photon absorbed or emitted. This is why absorption and emission spectra have very discrete lines, which we will go into in a later unit. Now let's talk about one of the most famous discoveries about photons, which is the photoelectric effect. What scientists found was that when you shine a light on a piece of metal, nothing happens unless the light has a high enough frequency. Once you pass that threshold of frequency, electrons get ejected from the surface. And it's like photons are zapping electrons off the metal. And this was a big deal because it showed that light behaves not just like a wave, but also like a particle. Each photon carries a specific packet of energy. And if you have enough energy, you can actually emit off an electron from this piece of metal. So mathematically, we write this as hv, or Planck's constant times frequency, equals the kinetic energy of the electron and the binding energy. In other words, the photon's energy is used first to free the electron, and whatever is left over becomes the electron's speed. All right, here's a closer look at the photoelectric effect with potassium metal, which requires 2.0 eV to kick out an electron. EV just stands for electron volt. So as you can see with these 700 nanometers, it does not have enough energy to kick out an electron from potassium metal. So no matter how bright that red light is, it doesn't matter. It doesn't possess enough energy to actually emit or eject one of the electrons from the potassium metal. Now looking at our other two waves of light, we have 550 nanometers and we have 400 nanometers. Now you should know at this point that when we have a smaller wavelength, which is our nanometers, it's going to mean we have a higher frequency, which means more energy. So looking at the green versus the purple, we should know that the purple is going to have much more energy, which means when it hits this potassium metal, it's going to eject an electron, and this electron is going to have a lot more kinetic energy than our green electron because it is a shorter wavelength or a higher frequency. So let's practice applying the equation E equals HV, which is a very common application of this lesson in the AP Chemistry exam. So it says, which of the following is closest to the frequency of the light with photon energy of 3.3 times 10 to the negative 19th joules? So this is obviously a multiple choice question that I turned into a free response. So we're just going to solve for the frequency when we were given energy in joules. So since we were given energy and we always know H because it's a constant, we're going to be solving for V, which is frequency. So that's going to be energy divided by Planck's constant. So we are given our energy at 3.3 times 10 to the negative 19th joules. And Planck's constant is going to be 6.626 times 10 to the negative 34th joules per second. I don't have my fancy calculator with me, so I'm going to do this old school. 3.3 divided by 6.626 is going to give us 0.498. Then with our exponents, we bring 10 to the negative 34th to the top, which gives us positive 34. So if we do 34 minus 19, we're going to have an exponent of 15. And in order to get this into scientific notation, we need to move that decimal point, so we will have 4.98 times 10 to the 14th, and this would be per seconds or hertz, however you want to do it. So it honestly depends on what you're given in the question, so either one of those would work. They equal each other. All right, this one says solve for energy in joules, and we're given 510 nanometers, which is our wavelength. So we are solving for energy, and we are given lambda or wavelength. So looking at our reference sheet with these variables, we know we're solving for E, and we know we have lambda, and in both of these equations, we have frequency. So we can set frequency equal to each other and then make this one equation. So on the bottom one, it would be frequency equals C divided by wavelength, and then we can plug that in for frequency here. So our total singular equation that we can use is E equals H times C divided by wavelength. So H is Planck's constant, 6.626 times 10 to the negative 34th, and that's joules times seconds. C is speed of light, which is 2.998 times 10 to the 8th meters per second. And then wavelength, because I am in meters in the numerator here, I have to change nanometers to meters. 1 nanometer is equal to 1 times 10 to the negative 9th meters. So I can take my 510 and just slap on times 10 to the negative 9th, and that's going to give me meters. for math purposes, just because I want to, I'm going to put it into scientific notation. So my wavelength would be 5.1 times 10 to the negative 7th meters. So as you can see with our units here, meters and seconds are going to cancel out, so we're only left with joules for our final answer, which is what it asked for in the question. So now let's go ahead and do the math. Again, I don't have my fancy calculator with me, so just bear with me in how I'm doing this. First, I'm going to do 6.626 times 2.998. Then I have to look at my exponents here. So I have negative 34 plus 8. That's going to give me 10 to the negative 26. And then on the bottom, I have my 5.1 times 10 to the negative 7th. So I have 19.8647 divided by 5.1. And then I bring my 10 to the negative 7th to the top, which would give us positive 7. So now if I add those two exponents together, I have 10 to the negative 19th. And I know I am left with joules. So this would be our final answer. If you wanted to do to the correct amount of sig figs, I am given 2 sig figs. So technically my correct answer would be 3.9 times 10 to the negative 19th joules. In an experiment, a photon with a frequency of 7 times 10 to the 14th per second was absorbed by a sample. What is the approximate energy of this photon? So again, we are looking for energy and we are given frequency. So we don't have to combine equations here. We're looking for energy, we're given frequency. So we want to take our frequency and multiply it by Planck's constant. So all we would do in this question, I would put this right in my calculator, but I'm going to write it out for you just in case. E is going to equal 6.626 times 10 to the negative 34th joules times seconds times our frequency, which is 7 times 10 to the 14th per second. So seconds are going to cancel out. We're left with joules. So we would just do 6.626 times 7. That's going to give us 46.382. And then looking at our exponents, we have negative 34 plus 14. So that's going to give us times 10 to the negative 20th. And then obviously this is not in scientific notation. So our final answer would be 4.64 times 10 to the negative 19th. And that is going to be closest to A. All right, so this question, it says the frequency and energy ranges of photons in some parts of the electromagnetic spectrum are given in the table above. Which of the following could be the energy of a photon in the visible range? So we're looking at energy and we're looking at visible range. So we're trying to find this question mark here. Now, in order to do that, we need to look at what we are given. We are given the ultraviolet, which is of a higher frequency or higher energy, and we are given infrared, which is of a lower energy. So we want to be somewhere in between the lowest of the ultraviolet and the highest of the infrared. So somewhere in between 5 times 10 to the negative 19th and 3 times 10 to the negative 19th. And there is only one option, which would be C, 4 times 10 to the negative 19th. All right, and for our last question of this lesson, which of the following is closest to the frequency of the light with photon energy of 3.3 times 10 to the negative 19th joules? So we're given energy and we're solving for frequency, which are in the same equation. So we are just rearranging that formula to solve for frequency, which would mean energy over Planck's constant. So energy is given to us at 3.3 times 10 to the negative 19th joules. Planck's constant is always the same, 6.626 times 10 to the negative 34th joules times seconds. So my joules cancel out and I'm left with seconds to the negative first, which is the case for all 4 of my options. So I don't really have to worry about that. Then I'm going to take my handy dandy phone calculator and take 3.3 divided by 6.626, which is going to give us essentially 0.5. I can see that all of my options are 5, so I know that's the right calculation. And then I need to worry about my exponents. So I'm going to bring times 10 to the negative 34th to the numerator. So now essentially I have times 10 to the negative 19th multiplied by 10 to the positive 34th. And when I am multiplying exponents, I'm actually adding them. So positive 34 minus 19 is going to give me times 10 to the 15th. Well, this is clearly not in scientific notation, so I need to change that. So my final answer would be 5.0 times 10 to the 14th seconds to the negative first, which means my answer is C. All right, I hope that helped and made sense. I hope you have a great day. Bye.